Dear students, welcome to the next lecture of digital communication. So today we will continue our discussion about the optimum receiver for binary data transmission. So so far we have been covering a lot of concepts. So let me recap whatever we have covered so far. So we have covered the signal space concepts. Okay, so we learned that given any time domain signal, we how to represent it as a vector point in an n-dimensional space. We have learned about the Gram-Schmidt procedure to obtain the basis functions of the signals. We have learned how to represent the received signal in presence of AWGN in the same signal space, and then we also derived the optimum decision rule so that the probability of error is minimized. And by now we all know that the optimum decision rule is the minimum distance receiver. And then we also learned about the matched filter representation of the optimum receiver. Okay, so also towards the end of the last lecture we were discussing that if you can rotate the set of axes that you have to represent your signal space by an angle theta, such that the new set of axes is aligned in a way that the new phi 1 axis, which is denoted by phi 1 hat, is perpendicular, or actually the perpendicular bisector of the line joining the two signals. Then you can represent the optimum receiver with just one matched filter. Okay. So this was the rule of the rotation. So you have the original axis, and rotating it through an angle theta will give you a set of transformed axes which are related to the original axis through this transfer matrix. Okay, so which is in terms of theta. Okay, so if you do that, then you can adjust the optimum decision rule like this in terms of the received signal in the transformed axis, which are denoted by the components of the received signal as R1 hat, R2 hat, R3 hat, and so on. And also the transmitted signals and the noise is represented with a hat in the top in the transformed axis. Okay, so you can see that the signals that were transmitted, they don't change their relative position, they are fixed. But since the axis gets rotated, they have new set of coordinates in the transformed axis. Okay, so now they have a new set of coordinates in the transformed axis. So these coordinates were equivalent to these in the original axis. Okay, same for this signal. So in the transformed axis you have S11 and S21 with a hat, and these were equivalent to the coordinates in the original axis. Okay, so so nothing has changed, the signals remain the same in terms of their relative position in space, but since the axis has changed, the way we represent these signals in the transformed axis has also changed in terms of this transformed coordinates. And the optimum decision rule can be adjusted for this transformed axis, okay, and you can have this optimum decision rule, which is just in terms of the second component of the received signal, okay, which is denoted as R2 hat in the transformed axis. So only thing you need to check is whether your R2 hat, which is the second component of the received signal in the transformed axis, whether it is greater than or less than a certain threshold t. And the value of the threshold is given in terms of all the quantities that you know already. You know the a priori probabilities, you know N0, the noise power spectral density, and you also know the coordinates of the signals in the transformed axis, okay. So you can write this expression, which is the expression for threshold, and you can just check whether your R2 hat is greater than this threshold. If so, then you decide a 1, and if it is less than, then you decide a 0. So with this arrangement, you can just have a single correlator which is correlating the received signal with respect to the phi 2 hat, which is the second axis of the transformed coordinate system, and then after sampling you get R2 hat, and you are passing it through a comparator circuit to check whether it is greater than a threshold or less than a threshold, and then you make your decision. In terms of matched filter also, you can have a single matched filter that approximates this correlator, and then you can have R2 hat, and you are comparing that with the threshold. Okay, so so we will extend this concept now, but before that, let's do a class exercise. Okay, so you are asked that show that regardless of the angle theta, the set phi 1 t hat and phi 2 t hat is also an orthonormal basis set. Okay, so let's try to solve the first part. Okay, so let's say you have this phi 1 hat t, which is your cosine of theta times phi 1 t and sine theta times phi 2 t. So this comes directly from this relationship that we had. Okay, so this comes directly from this relationship. Okay, so we are writing the expression of phi 1 t hat and phi 2 t hat from that relationship, and you have the new set of axes defined by this orthonormal basis functions phi 1 t hat and phi 2 t hat in terms of the original phi 1 t and phi 2 t. Actually, we have to show that these are also orthonormal. Okay, so that is what we need to show. So to show that, we have to ensure that this integral is 0. Okay, so if we write this integral, so the left hand side of this integral is basically I just multiply these two terms, so we will get minus cosine theta sine theta phi 1 square Okay. Then we have cosine square theta phi 1 phi 2. Okay. Then we have minus sine square theta phi 1 phi 2, and finally we have sine theta times cosine theta times phi 2 square. Okay. So the entire integral turns out to be this. So now, if you see from the property of the original set of axes, so integral of phi 1 square t is 1. So this particular term will be minus of cosine theta times sine theta. Since this integral is 1 because of the orthonormality of phi 1 and phi 2. Similarly, this term will be 0 because of the orthonormality of phi 1 and phi 2. Then the next term will be also 0, and then the final term will be sine theta times cosine of theta, because again this integral is 1, right? So you can see that we cancel these two terms and then you have a 0. So therefore this integral is indeed 0. So therefore these two phi 1t and phi 2t hat are orthogonal. So this says that they are orthogonal. But whether they are orthonormal or not, we have to check by checking if phi 1 hat square t dt is equal to 1, and the same is true for phi 2 hat square t dt. And if you apply this rule, if you square phi 1 hat square, if you square phi 1 hat t and then apply these rules for the original integrals, original phi 1 and phi 2, you will see that this integral will also be equal to 1. Okay. So therefore you can see that phi 1 and phi 2, so let me do one for you. Let's say phi 1 hat square t is basically cosine square theta phi 1 square t plus sine square theta phi 2 square t plus twice cosine theta sine theta phi 1 phi 2. Okay. So now if you take the integral of this with respect to t, then this term will give you cosine square theta, this term will give you sine square theta, because these two integrals will be 1 because of this property, and this term will give you 0. And then cosine square theta plus sine square theta is a trigonometric identity which gives you 1. So you can see phi 1 hat square dt is indeed 1, and you can show the same for phi 2 hat square dt. So therefore we can say that these two are orthonormal. Okay, so let's now move to the second part of the problem. So the second part of the problem says that what are the values of theta that make phi 1 hat t perpendicular to the line joining S1t and S2t. And for these values of theta, mathematically show that the components of S1 and S2 along phi 1 hat, namely these, are identical. Okay, so for this part, to show that that phi 1 hat t is perpendicular to the line joining S1t to S2t, what you have to do, so let's say you want to show phi 1 hat t is perpendicular to the line joining S1t and S2t, right? So in vector norms, in vector notations, all you need to show is that this integral is 0. Okay, so this basically gives you the equation of the line joining S1t and S2t. Okay, or the vector that shows the line joining S1t and S2t, and this is basically simple to show. So let's say this is my S1 and this is my S2. Okay, so these are two vectors in this direction. Okay, so if you do S1t minus S2t, then basically what you are trying to achieve is this line. Okay, so so S1, this line is in vector norm S1t minus S2t. Okay, so this vector needs to be shown perpendicular to this vector, and that can be shown by setting the dot product to 0. Okay, so again, if you write the expressions of phi 1 hat t, so phi 1 hat t was basically cosine theta phi 1 t plus sine theta phi 2 t. So phi 1 hat t is cosine theta phi 1 t plus sine theta phi 2 t, right? And then this part is you can write S1 as S11 phi 1 t plus S12 phi 2 t, and S2 is S21 phi 1 t and S22 phi 2 t. So this is the whole integral. Okay, now if you collect all the terms that are with phi 1 and all the terms that are with phi 2, you will have this integral as cosine theta times S11 minus S21 phi 1 square t dt. Then you have sine theta times S12 minus S22 times phi 2 square dt. And then what are the other cross terms? So the cross terms will give you 0 anyway, because whatever be the integrals associated with phi 1 and phi 2, whatever the coefficients are here, these integrals will give you 0 anyway. Okay. So this will come down to cosine theta times S11 minus S21, because this integral will give you 1 plus sine theta times S12 minus S22. Okay, and this has to be 0 for this condition to satisfy, for this phi 1 t hat to be perpendicular to the line joining these. Okay, so this can be written as tangent of theta equal to minus of S11 minus S21 divided by S12 minus S22. Okay, and therefore from this you can get theta as tan inverse of this term. Okay, so this is the condition on theta that will make you the phi 1 t hat, which is the new phi 1 axis in the transformed coordinate, to be perpendicular to the line joining S1t and S2t. Okay, so this, if you rotate the axis by this angle theta, which is given by this equation, which is purely in terms of the coordinates of the signal in the original axis, so you know how much you have to rotate, so that in the new axis you will have phi 1 hat t perpendicular to the line joining S1 and S2t, and if this happens, then you can have one single matched filter to represent your optimum receiver. Okay, so now what are the values of theta that makes? Okay, so we have just done this. So for these values of theta, mathematically show that the components of S1 and S2 along phi 1 t hat, namely this, are identical. So if you now calculate S11 hat and S12 hat, that can be calculated. So basically, let me now use this slide. So now in this case, if you now want to write S11 hat, which is nothing but S1 times phi 1 hat dt. Okay, or S1 S1t phi 1t. Sometimes I just tend to omit this t in the parenthesis just for simplification, but they mean the same. So in this case, you can write it down like you can write S1. So let's say you can write S1 as S11 times phi 1 plus S12 times phi 2, and phi 1 as cosine theta of so phi 1 hat is cosine theta of phi 1 plus sine theta of phi 2. Let me cross check. Yes, cosine theta of phi 1, sine theta of phi 2. So then again you can do this simplification, and you can show that this integral is S11 times cosine theta plus S12 times sine theta. Okay, and you can plug in the value of theta from what you have just calculated, and in that case you can finally calculate S11 hat. Similarly, you can calculate S21 hat, and if you do everything correctly, you can indeed show that these two are identical. I leave this as an exercise for you. Okay, so let's move on with the receiver performance when we have just one matched filter representation. So so let's say if you rotate the axis, by the way, so as I said previously, so nothing changes, the signals remain the same, the signal's original position doesn't change, only the axis changes. Okay, so this means the signal in time domain, whatever they were, they remain the same. Only thing is that you can define many phi 1s in terms of phi 1 or phi 1 hat or whatever to represent these signals. Actually, the point is that given two signals S1 and S2, you can define any axis. You can define an axis like this. You can also define, let's say, a set of axes like this. Okay, you can define any axis as long as they are orthonormal to each other. You can define any axis like this. Okay, and the signals can be represented in these axes accordingly with a new set of coordinates. Okay, but the signals relative positions are same. So that's why while we are trying to find out the receiver performance, we will always care about a particular representation of the signal which eliminates the requirement of two matched filters, because we saw that by making some adjustments to the axis of the signal space, we can represent the receiver with a single matched filter. So from now onwards, we will use this concept. We will analyze the receiver performance by assuming that the signal set is represented in such a way that we only have one matched filter. Okay, and we will see how the probability of error can be calculated from that. Okay, so let's move on with this philosophy. So as I said, we are assuming that we always have a situation where we can represent the signals in a set of axes that can be that can finally give us a receiver with a single matched filter. So this is the case, let's say. So in such a case, we are only observing the R2 component of the received signal, or R2 hat, let's say, because it has been transformed. And then you have a decision boundary which is determined by your threshold. Okay, so this threshold has this expression. So now you are checking whether your R2 hat is in this region of the boundary or in this region of the boundary. If it falls in this region, then you decide that a 1 was transmitted. If it falls in this region, then you decide that a 0 was transmitted. Okay, and then if you try to plot the PDFs, the conditional PDFs of R2 hat with respect to 0 transmission and 1 transmission, then they are Gaussian distribution like this, with means S12 hat for this one and S22 hat for this one. Okay, so so this is the case. So R2 hat, let's say, will be basically S12 hat plus W W2 hat. Okay, so if the signal 1 was transmitted, or if the signal 0 was transmitted, then this is the case for R2. If your signal 1 was transmitted, then R2 hat will be S22 hat plus W2 hat. Okay, so this is the noise for both the cases. So we have already seen that since the received signal component is also Gaussian, because the noise is Gaussian, but the noise was zero mean, but since we are adding a fixed term to the noise in the form of these signals, the received signal will be Gaussian with these means. Okay, so this we have already established in the previous lectures. Okay, so therefore when you draw the PDF for the 0 transmission case, you have S12 hat as the mean of the Gaussian distribution, and for the 1 transmission case you have S22 hat as the mean. Okay, so far so good. So now let's see, if I want to calculate the probability of error, so this can be written as this, which again we have seen before, and then this can be broken down into the conditional probabilities plus this term which is the a priori probability, same for this one, and the a priori probabilities for 0 is P1 and for 1 is P2. Okay, and the conditional probabilities are defined by these. Okay, so this is the PDF of R2 hat given 0 was transmitted, and we integrate it from t to infinity, because the error occurs, this error, like 1 is decided when 0 was transmitted, this occurs only when the received signal component R2 that we are observing falls in this region. Okay, so if it falls in this region, this is the region for 1. Okay, this is the region for 1, and this is the region for 0. So if I am transmitting a 0 but my received signal falls in this region, then I am making an error, and that probability of error is anything that falls in this region from this value t, which is this threshold or the decision boundary, to infinity. So t to infinity of this conditional PDF. Okay, so in other words, this is the area that we are interested in. So which part of this conditional PDF falls beyond my decision threshold boundary? So this is the area B, and this is the area for this conditional probability. Similarly, for this conditional probability, this is the area that I am looking for. Which part of this PDF falls in the decision region of 0? Okay, if that is the case, then we are making an error. So this is the area A here. Okay, so now let's see how do I calculate these areas. Okay, so if you write the expression for the conditional PDF, which is a Gaussian distribution with mean S12 hat and variance n0/2, then this is the expression that you get. And for the second part, you get similarly this expression. The first integral is between t to infinity, which is this area, and the second integral is between minus infinity to t, which is this area, okay, this one, okay. So now if you make a change of variable, like let's say if you replace this term with lambda, okay, the first integral can be written as this, okay, and this can be written as a q function. So q function, so this is a general expression of a q function, so you can write it in terms of a q function. I am coming to the concept of q function later, but right now just appreciate that mathematically this expression is written as this, okay. Similarly, the second integral can be written as 1 minus the q function of this term, okay. So now if you calculate the probability of error, okay, so q function is defined as this. So integral of this term from x to infinity, this is nothing but the area under the curve from x to infinity for a Gaussian distribution with 0 mean and unit variance. So sigma square is 1 for this and mu is 0, okay. So for this, if you calculate this area, then this is termed as a q function, and if you plot qx with x, then you have a graph like this, okay, which is sharply decreasing with x. So going back to the probability of error expression, so if you set p1 equal to p2, then your threshold expression reduces to this term, okay. You remember that in your threshold expression it was this term plus some log of p1 by p2 type of term with some constant here, okay. So this p1 p2 equal means this will be 0, this term will be 0. So your threshold is only this part if your p1 is equal to p2, okay. And we have an interesting property of q function, which is qx is equal to 1 minus q of minus x, okay. So if you apply these two in the original expression for probability of error, okay, which is this term, basically the original probability of error is p1 times q of t minus s12 hat n0 by 2 plus p2 times 1 minus q of t minus s22 hat divided by n0 by 2, okay. So so your p1 is equal to p2, which is equal to half, because your p1 and p2 are equally likely, okay. So this expression will be probability of error will be half of q of something plus 1 minus q of something, okay. So if you put your threshold, which is now equal to s11 hat plus s12 hat by 2, sorry, s12 s22 s12 hat plus s22 hat by 2, and fit this here, then this will simplify to this term, okay, with also application of this property. Okay, so I leave it to you as an exercise to check whether this is indeed equal to q of this particular term. Okay, so now if we move on and further simplify this s22 hat minus s12 hat, which is nothing but the projection of s2 on phi 2 hat and projection of s1 on phi 2 hat, and then simplify this expression, then you see that you obtain this term, which is basically the distance between the two signals. So this is an interesting result. Okay, so then we can write the probability of error expression as the q function of the distance between the two signals divided by 2 times the noise RMS value. Okay, so noise root mean square value, which is the noise power spectral density, square root of that. So if you can remember this formula, so this is true for any pair of signals, and this expression you will see later on from this point onwards in this digital communication module, you will be using it a lot. So this is for a binary communication where you have two signals S1 and S2, and it says that the probability of error just depends on how far the two signals are, okay, or how dissimilar the two signals are. So distance between the two signals will be low if the two signals look very close. Okay, so for example, let's say my S1, if my S1 looks like this and my S2 also looks like this, then S1 minus S2, or the distance between these two signals, is 0. So if you want to plot these two signals, it will be the same 2 points, okay, because they are very similar. They are exactly the similar, let's say. So it will be S1, and then on top of S1 you will have S2, the same point for the two signals. So therefore the distance between S1 and S2 is 0 if they are all exactly similar, okay. And this distance increases if the signals look different, okay. So let's say if I have S1 like this and your S2, let's say, is like this, okay, then if you manage to plot these two signals in the signal space, they might look like this, okay. Let's say S1 and S2 might look like this. So you see the distance here is some finite value, okay. So the more different the two signals look, or the more dissimilar the two signals, the greater is the distance between these two signals, okay. So so which means that if the distance between the signals is very high, because this is the numerator of the q function, and we have seen that with the increased value of x, the qx values falls very sharply, okay, like this. So more you increase x, the lesser will be your Qx, and Qx determines your probability of error. So you have to have larger x to have a very low probability of error. Okay. So in other words, you have to increase the distance between the two signals, which translates to the fact that the more dissimilar the two signals are, like for binary communication, you are choosing S1 for 0 transmission and S2 for 1 transmission. If you choose S1 and S2 in such a way that they look very dissimilar, very different, then the better it is in terms of probability of error. So you will eventually get a system which will give you a very low probability of error. Okay. So this is one form where, to maximize the distance between the two signals, one chooses them so that they are 180-degree phase apart. Okay. So in that case, your S2 will be equal to minus of S1t. Okay, and in that case, the distance between the two signals will be maximum, and this is called antipodal signaling. Okay, the error probability does not depend on the signal shapes, but only on the distance between them. So this is again very important. Okay, so so you will see for the next few lectures in digital communication, when we will do multi-level signaling, where you will have more levels rather than 0 and 1 and more signals to send, we will see that to calculate the probability of error, where we have multiple signals, more than just 2, we will be using this formula a lot to calculate the approximate probability of errors. Okay, so so this is true for any two pairs of signals. Okay, so Qx and error function. So there is another function called complementary error function, denoted by ERFCX. So they are related to each other in this form. So you can also express the probability of error in terms of a complementary error function also, which you might be using while you will do your MATLAB assignments. So let's move on. So let's do this example. So so we have phi 1 which looks phi 2 which looks like this, and phi 1 which looks like this, and two of your signals are given, S1t and S2t. S1t is for 0 transmission, S2t is for 1 transmission. So determine and sketch the two signals S1t and S2t. So you can just write down S1t by looking into this diagram, which is 2 times phi 1t plus 1 times phi 2t, and your S2t will be minus phi 1t minus twice phi 2t. So now you know how phi 1 looks, how phi 2 looks, so you can now draw based on this expression. So so the drawings will be like this. Okay, so see, they are writing the signals in terms of phi 1 and phi 2 just as I did, and then you can have a drawing like this. Okay, so let's look into the part B. The two signals S1t and S2t are used for the transmission of equally likely bits 0 and 1 respectively over an additive white Gaussian noise channel. Clearly draw the decision boundary and the decision regions of the optimum receiver. Write the expression for the optimum decision rule. So you have the two signals here, and basically the decision boundary is the perpendicular bisector of the line joining the two signals. So this is the two signals, and the line joining the two signal is this, and the perpendicular bisector is your decision boundary. Okay, and you can find the equation of this line. Okay, this line's equation in terms of the received signal components is nothing but R1 plus R2 equal to 0. Okay, this line. Okay, so this is the decision boundary. So therefore the decision rule is basically if your R1 is greater than or equal to minus R2, then you go for 0. So this is the region for basically R1 plus R2. This is the decision boundary. So this is the region where R1 plus R2 is greater than or equal to 0. Okay, so this is for 0 decision, and this is the region for which your R1 plus R2 is less than 0. So this is the region for 1 decision. So if R1 is less than minus R2, then you decide 1. Okay, let's see the part C of this problem. So find and sketch the two orthonormal basis functions phi 1 hat and phi 2 hat such that the optimum receiver can be implemented using only the projection of R2 hat of the received signal RT onto the basis functions phi 2t. So basically this is looking for that transformation by rotating through an angle theta, and that gives you only one matched filter receiver. So this is again basically if you rotate the axis by an angle theta which is minus pi by 4. So basically if your axis is rotated in this direction, these axes coincide with this line which was your original decision boundary, and the original decision boundary was basically the perpendicular bisector of the line joining the two signals. Okay, so if your axes are rotated in this direction, then the new set of axes, okay, the new set of axes will have a phi 1 t hat component, which will be also perpendicular bisector of the line joining the two signals. Okay, so therefore the rotation will be minus pi by 4, and if that is the case, then you can calculate the transformed axis using this rule, and you can get phi 1 t hat as this and phi 2 t hat as this. Okay, now let's see the next part. So consider now the following argument put forth by your classmate. She reasons that since the component of the signals along phi 1 t hat is not useful at the receiver in determining which bit was transmitted, one should not even transmit this component of the signal. This is interesting. So thus she modifies the transmitted signal as follows. So this is the modified signal. S1mt is basically the S1t minus the component of S1t along phi 1 hat t, and S2mt is S2t minus the component of S2t along phi 1 hat t. Okay, so clearly identify the locations of these modified signals in the signal space diagram. What is the average energy of this signal set? Compare it to the average energy of the original set. So if you calculate S1mt, which is, let's say S1mt is S1t minus the component of S1 along the phi 1 hat direction. So basically this will be S1t times phi 1 hat t dt. So this part you are subtracting. So you calculate this part. So phi 1 hat t is now given by this. So this will be S1t minus, if you multiply S1t with phi 1 hat t, you will get 1 over root 2 S1t times phi 1t, okay, plus 1 over root 2 integral of S1t times phi 2t, okay. So S1 times phi 1t is basically, this one is S11, okay, and this one is S12. So S11 was 2. So basically the final expression will be S1t minus, this is S11, so this is 2, 2 over root 2 is root 2, okay, and this one is S12, S12 was 1, so this will be plus 1 over root 2, okay. So so basically you are subtracting some constant from S1t, okay. So then S1t will be basically shifted a little bit and you will get an S1mt here. Similarly, S2mt can also be calculated like this, okay. So so now if you calculate the energy of the modified signals, then you will get these expressions. So this expression will lead you to the half of energy of S1 plus energy of S2 minus half of this term, and then this will give you 4.5 joules, okay. And the average energy of the original signals will give you 5 joules, okay. So since the distance between the modified signals is the same as that of the original signals, both sets perform identically in terms of bit error probability. So you remember the probability of error we just derived few slides back is the Q function of the distance between the two signals divided by this, okay. So if you look here, even with the modified axis, the distance remains the same. If this distance is d, then this is also d, nothing changes, okay. So the distance between the both sets of signal remains the same. So Q function of this two distances are the same. So if you calculate probability of error for S1 and S2, this will give you the same result as S1m and S2m, okay. So actually your friend was right who gave you this suggestion that you don't need, okay, you don't need the component of the signals along phi 1t. So so in terms of probability of error performance, these two are same, okay. But energy wise, the modified signals have less energy, okay. So the modified set is preferred due to its better energy efficiency, okay. So So the other set might have better timing or spectral properties, but that we are not interested right now. Um, in terms of energy, the modified set is better, and in terms of probability of error, both are same. So probably we will prefer the modified set. Okay, so now let me quickly go through the basic digital passband modulation. So, baseband transmission is basically conducted at low frequencies. So these are the actual information carrying signals. Okay, and passband transmission means the modulated high frequency versions. Okay, so usually we modulate a signal with a high carrier frequency, much higher than the highest frequency of the message signals. Okay, and in case of digital communication, um, we have different types of modulation. We call them amplitude shift keying, phase shift keying, and frequency shift keying. Okay, so these are the digital equivalent of your amplitude modulation, phase modulation, and frequency modulations. Okay, so let's quickly look into these types. So if you have a binary data stream like this, 1011100101, and the equivalent modulating signal is like this, then you can have a binary amplitude shift keying where you have a high frequency carrier when you have a 1 and you have a 0 when you have a 0. You can have BPSK where you have two high frequency carrier. One is an 180-degree phase shifted version of the other, corresponding to the fact that if it is a 1 or a 0. And for BFSK you have two high frequency carrier again, but the frequency of 1 is higher than the frequency of 0. So in terms of the signal space concepts, what you have learned so far, you can represent binary amplitude shift keying as your S1t is 0 when you are transmitting 0, and S2t is a cosine function 2 pi fct when you are transmitting 1. And you can represent these two signals in the signal space like this. So you can have S1t which is 0 and S2t here. Okay, so you can represent the signals with a single basis function phi 1t. Okay, you don't need two. Okay, and the distance between the two signals is your amplitude. Okay, so basically the distance of any signal from the origin of the signal space gives you the amplitude of that signal. Okay, and the square of that distance give you the energy of that signal. So this signal S2t has an amplitude of this, and S1t is 0 anyway, so it stays here, so it doesn't have any amplitude. So in that case, the distance between the two signals is also equal to the amplitude for BASK. Okay, and you can have a matched filter representation like this. Sorry, this is the correlation receiver, but you can also have a matched filter that will be matched to phi 1 like this. So this will be the impulse function of the matched filter. Okay, and you can have a decision boundary which is halfway between the two signals, a perpendicular bisector of the line joining the two signals. And if the received signal falls here, you choose 1. If it falls here, you choose 0. And you can calculate the probability of error by using that formula which we derived. So basically this is this is the Q function of the distance between the two signals. So distance between the two signals is square root of this term EBASK divided by twice the noise RMS bandwidth. Okay, so if you simplify this, this will be Q of EBASK divided by twice N0, everything under the root. So this is what is here. Okay, so see how you are using that concept of probability of error calculation and easily write down the expression of probability of error. So again, this is the power spectral density of BASK. For phase shift keying, we have two signals. One is minus V cos 2 pi FCT and the other is plus V cos 2 pi FCT. So there is a 180-degree phase shift, and you can represent the signals again using just a single orthonormal basis function, which is given by this, and you can have S1t and S2t which are equidistant from the origin, each of them having an amplitude square root of EBPSK, and then you can calculate the probability of error again by writing down that Q of the distance between the two signal in the numerator, and the distance between the two signal is basically E square root of EBPSK plus square root of EBPSK, so twice square root of EBPSK divided by 2 times the noise RMS bandwidth. Now if you simplify this term, this will give you 2 EBPSK divided by N0, which is already here. So see how easy it becomes to calculate the expression for probability of error for a binary transmission system. All you need is to calculate the distance between the two signals in the signal space and represent the Q function of that term divided by the noise, 2 times the noise RMS bandwidth. Actually the denominator is same for all cases. The only thing you need to calculate is the numerator, and this is just the distance between the two signals for any example that you take up for binary communication. So again, for frequency shift keying also you can have this arrangement, so where you can have two different frequencies, two carrier frequencies, they are different, F1 and F2, and let's say they also have a phase difference theta 1 and theta 2, and the minimum frequency separation for orthogonality when theta 1 is equal to theta 2 is 1 over 2 TB. So orthogonality means if we are trying to have a scenario where your, let's say this is your phi 1 and this is your phi 2, and let's say we want to represent signal S1 as this point and S2 as this, so they are orthogonal to each other, or they are perpendicular to each other. So that happens if you have delta F, which is F1 minus F2 equal to this, okay, 1 over 2 TB. When your theta 1 is equal to theta 2, when your theta 1 is not equal to theta 2, then the separation delta F or F1 minus F2 should be equal to 1 over TB, okay. And then you can determine the signals like this, as I just showed, and this is your decision boundary, and the probability of error can be calculated again as the distance between the two signals. So in this case, the distance between the two signals is this distance, which is written as, let's say, d21 square is basically this term square plus this term square. This is basic geometry. So this is like this term, this distance is EBFSK, and this is also EBFSK. So you have twice of this term, right? Now if you put that into the formula, so your probability of error is basically Q of the distance between the two signals, which is 2 times EBFSK divided by this term, which is always fixed. So now if you simplify this, this will be, sorry, d21 square is this, so this will be a square root. So now if you simplify this, this will be Q of EBFSK by N0, which is already written here. So you can easily calculate the probability of error like this. And if you compare the performance between these three schemes, BPSK, BASK and BFSK, then you can see that your BPSK performs the best. Okay, BASK and BFSK have kind of similar performance, and BPSK performs the best. Okay, so why this is happening, I will explain it in later, but before that I want you to reflect on this and find out the answer yourself. Okay, and then I will explain if you cannot find out the answer to yourself. Okay, so this is a thought exercise for all of you. Okay, so I'll stop here today and I will see you in the next video lecture. Thank you.